Hello, Jim Winslow here. Welcome to Winslow Physics. In my last two presentations we discussed the variable speed of light and created an equation relating gravity to the variable speed of light. In this presentation we take these concepts further and create an equation for the speed of light and also come up with the concept of the free space speed of light, which is the maximum speed of light you can ever achieve. So here's the standard gravity equation. This is something you'll see in high school physics over here. If you plug in the radius of the Earth, the mass of the Earth, the universal gravitational constant, you will get 9.8 meters per second squared, which is the acceleration due to gravity on the surface of the Earth. Here's another version of the equation, which is just basically algebra, where minus gm over r is the gravitational potential. This is something you might see in college physics. And again, this is something even a little more arcane, but it's the same exact thing, except for it's using vector algebra. These are the absolute value sign, and so all this is true standard gravity equation. Now let's compare the new equation for gravity to the standard gravity equation. You see how they look kind of similar? Well, here we have replaced c with cl. I now call the variable speed of light, wherever you are, cl for the local speed of light. Let's compare these two equations. You go here, and you go here. Then you can add a constant because this is a derivative. This upside down triangle with an arrow is a derivative, so you can add a constant to the equation. You come up with the final equation. CL squared equals CFS squared minus 2gm over r, where CL is the local speed of light, CFS is the free space speed of light. And I just want to remind that C in this presentation is going to be the surface of Earth speed of light. What does this all mean? Well, here's the equation. Let's say you have a large massive object. You plug m into the equation. R is the distance from the center of the large massive object. As r goes to infinity, this term goes to 0 and CL approaches CFS. Okay? As r gets smaller, this term becomes larger, subtracts from CFS squared, and CL squared becomes less. So as you approach the large massive object, the local speed of light decreases. And as you go to infinity, the speed of light approaches CFS, which is the free space speed of light. So we're going to try to figure out what that free space speed of light is. So to do so, I'm going to approximate the light speed difference. Okay, so here's the equation again. Rearrange to do this. A little bit of algebra to do this. Divide both sides. You get CFS plus CL. Assume that CFS and CL are both close to the speed of light on Earth. And because you're dividing by that, we are now allowed to do this, 2c, 2gm. The 2's cancel out. You get gm over cr. Let's call CFS minus CL, which is always positive because CL is always less than CFS. So we have delta C approximately equals gm over cr. We can then have multiple massive objects. This is just a summation sign for multiple massive objects where we just add all the terms together, and then we can do some interesting math. Here's some constants for you in case you don't want to look them up yourself. But basically, I found out that on the surface of the sun, due to the sun's mass and the radius of the sun, the speed of light is 636 meters per second slower than the free space speed of light. Now, because we can't really measure the speed of light on the sun safely, I suggest you never try this because the sun is really, really hot and it will pull you in. But we can do it on the Earth. So on the Earth, the speed of light difference due to the Earth is 0.2 meters per second on the surface of the Earth. But what about the sun? It turns out that the sun actually makes a greater contribution. So the sun, the distance from the sun's mass, to the Earth results in a delta C of 2.9 meters per second. Add these two together, you get about 3 meters per second, because we know what the speed of light on Earth is. We can now put in the equation and approximate what the free space speed of light is. It's about 3 meters per second. Okay, so the free space speed of light out between galaxies is faster. How much faster? Not a lot, about 6 miles per hour. So here's the postulate for here's the equation for the free space speed of light. We're a single massive object. Okay, the local speed of light, local to free space speed of light, minus 2gm over r. Here's the general equation for multiple massive objects. And here's the final one. The free space speed of light is approximately 3 meters per second faster than the speed of light measured on the surface of the Earth. This concludes the presentation. Stay tuned next time where we discuss gravitational redshift. Thank you very much.